Good afternoon, everybody. My name is Daping Chu. I'm Director of CAPE, and welcome to this CAPE Advanced Technology Lecture. Today, we are very honored and with great pleasure, we introduce Dr. Jennifer Schooley. She is the Director of the Cambridge Center for Smart Infrastructure and Construction at the University of Cambridge, of course. She works with colleagues in industry and academia to demonstrate how better data and information from a range of sensing systems can be used to improve our understanding of infrastructure, leading to better design, construction, and asset management practices, and to improve our understanding of how our infrastructure serves our communities. This has included projects in structural health monitoring, whole life value-based asset management, and development of digital twins to support decision-making. She has contributed to a range of industry guidance, policy documents, and wider industry publications to raise awareness of the need for digitalization. Jennifer serves on BSI and ISO committees, developing standards for digitalization in the built environment. And she is also a member of the UK's Digital Framework Task Force and a member of the Infrastructure Client Group's Digital Transformation Task Group. Jennifer was lead author for the Carbon Reduction Code for the built environment. In 2019, Jennifer was awarded a OBE and the ICE President's Medal for services to engineering and digital construction. Jennifer has a PhD in materials from the University of Cambridge, so she's local. And the title of her lecture is Development in Smart Infrastructure and Construction. Jennifer, please.
Thank you very much, Daping. I will just share my screen. Can you see the slides there?
Yes.
Brilliant. Okay, I will crack on. So welcome everybody to this lunchtime talk. Those of you who are based in CAPE may well recognise this picture. This is the civil engineering building out the back of CAPE where I am currently standing. So I'm back at work in the real world. And as Daping said, I'm going to be talking about developments in smart infrastructure and construction. So the content of my talk, I'm going to actually start with why infrastructure matters, because I think it's important for us to reflect on that. And I do this even when I'm talking to civil engineers. I'll explain why in a moment. Talk about infrastructure as a system of systems, and then the insights that we can gain from data through digital twins and cyber physical systems. I'm going to talk a little bit about whole life value-based asset management, and I'll explain what I mean by that when I get to it. How we can use digital twins for structural health monitoring, and then I'm going to talk about digital twins in the context of cities and the challenges around delivering public value. And if I've got time, I will briefly touch on carbon as well. So a sort of fairly fast journey through a whole range of topics. But as I said, to start with, why does infrastructure matter? And even as civil engineers, we don't always stop and reflect on why infrastructure is important. So I thought it's worth just having a look at some images. So these images here are from Kibera, which is an informal settlement in Nairobi in Africa. They're not dissimilar to many informal settlements all over the world. And what's notable about these is that there is essentially no formal infrastructure. So there's no formal drainage system, no formal clean water supply system, no formal power system, and certainly no formal waste removal infrastructure. So what you end up with is open sewers running down the middle of streets, very patchy access, if any, to power, people having to pay to get water from the standpipe and so on. And these are not very healthy and happy places to live. If you look on the bottom picture, on the left-hand side there, that open grey door is the entrance to a school. So imagine having had to go to school and you step out and you're essentially stepping straight into an open sewer. This is not an environment that encourages human flourishing. On the other hand, formalised infrastructure yields places that look like this. They're much more managed, they're much cleaner, notionally much healthier places to live. They have, nice green spaces available for recreation. People in a city like this is obviously New York, have access to power 24/7, clean water 24/7. They have access to the internet. And this is a much healthier, more pleasant place to live and work and spend time, go to school, etc. So fundamentally, infrastructure facilitates sort of modern, healthy, flourishing human societies that we've all got used to. That said, infrastructure isn't necessarily in a smart, swanky city like New York. It can be in very different places. So this is a picture of a refugee camp in Jordan. And the reason I wanted to put this up is, obviously the people who are living in this refugee camp have fled from unimaginable horrors through a civil war. They're displaced from their own country. But the environment they're living in is at least much less challenging than the images I showed you of Kibera. So at least while they're trying to rebuild their lives, they have access to clean water, they have access to power, they have access to reliable shelter, they almost certainly have access to the internet, they have paved roads. So although their lives are, upended and in turmoil, they are at least supported in rebuilding their lives by the services that good infrastructure provides. And that really is why I want to talk about infrastructure today, because it is so important to everything that we do as humans. And it's very important in the delivery of the UN Sustainable Development Goals. So the things I've highlighted in red here, clean water and sanitation, affordable and clean energy, obviously infrastructure itself, and sustainable cities and communities are all absolutely clearly directly associated with infrastructure. But infrastructure also has an impact on many of the other sustainable development goals. So it transforms poverty. With good infrastructure, you have access to healthcare, to education, and all the things that go with that help pull people out of poverty. It improves health and well-being. So when Sir Joseph Bazalgette made his huge intervention in London and essentially built the London sewage system back in the 1860s, he transformed the public health of the city, and it's regarded as the biggest public health intervention, the most effective public health intervention that's ever been made in London. The city was rife with cholera at the time, and by introducing decent sewerage and thereby enabling also access to clean water for people, because wells were no longer being polluted, he transformed the health of everybody in London. It's also vitally important for work and economic growth. So you need good infrastructure in order to encourage investment into a city, to enable workplaces to be placed there, but also you need good infrastructure to enable access to work and to education. You need good transport infrastructure, for example. It reduces inequalities. And when designed right, infrastructure can help reduce consumption and encourage responsible production, and also help us address climate action. That said, for those last two, if we get infrastructure wrong, it can contribute to the problems of resource use and climate change. So we need to be cognizant when we're thinking about both maintaining and managing existing infrastructure and designing new infrastructure of our impact on the environment. So that's why infrastructure is important. The other thing to understand about infrastructure is that it's pretty complex stuff. It is what I like to call a system of systems. So our infrastructure has sort of evolved over the last couple of hundred years, certainly in the UK, where I'm speaking from. And it is this complex sort of interweaved system of systems of water, transport, energy, buildings, ICT, and they all depend on each other and interact with each other. So, we have no water without power, particularly in the part of the world that I live in, where it's very flat. So all of our water is pumped, there's no gravity systems. We have no energy without ICT. Our transport systems increasingly rely on ICT and obviously rely on energy, and so on and so on and so on. So all of these things kind of lean on each other. And they've evolved, as I say, over the last 2 centuries or more, and not necessarily in a fully planned way. So the infrastructure we have today isn't the result of a single-minded plan that was set up back in the 19th century. Things have evolved as they've been needed. So we've added to this infrastructure system, and we continue to add to it in a sort of piecemeal way as need arises. And we need to keep it in operation effectively indefinitely. You know, it's very rare for us to take any piece of infrastructure out of operation. Only if something has been completely made obsolete do we take it out of operation. But even, as someone said to me the other day, even the canals, which you might regard in the UK as being obsolete as a form of transport, actually now perform a whole range of other services. So they create leisure opportunity, they provide ecosystem services by providing habitats for wildlife and so on. So even obsolete infrastructure often still has a function. And the crucial thing, particularly that I say to civil engineers, is that when we build new things, so each year we add about 0.5% by value to this complex system of systems in a developed economy like the UK. But even in a place that's developing quite fast, you're still only adding new stuff to the existing system at a relatively slow rate. So we really need to think about, if we're building new projects like, you know, High Speed 2 in the UK, we really need to, oh, sorry, there's a lot of background noise. Could someone mute themselves, please? Sorry, I need, Miguel, can you mute yourself, please? Thank you. Yeah, so as I was saying, we really need to think about our infrastructure as this complex system of systems and manage it in that way. And when we're building big new projects like High Speed 2 or Tideway, the two of the big projects that are going on in the UK at the moment, even though they're huge and they're costing billions and billions of pounds, each of them is only a small intervention on a much bigger system that's currently running. And these systems actually provide us with services that support our domestic, economic and leisure activities, support all the things that we do in our lives, and they create social, economic and environmental outcomes. So infrastructure is a system of services as well as a system of systems. So it's very important that we take a whole life perspective on this infrastructure, both as we're designing and building it, but also as we're using it and operating it and managing it. So how long is this asset expected to be used for? Often the answer to that is indefinitely. If we're building a new asset, should we invest a bit more carbon now to save carbon over the life cycle? Well, that depends on how long the asset will be used for. So if we get that calculation wrong, we can overinvest in carbon. And that's important because carbon remains in the atmosphere for 100 to 200 years. Can we make anything that we're building more energy efficient? How can we make it easier to maintain so that maintenance uses fewer resources and is quicker and easier to do so that we can keep our infrastructure operating at the required level? All of these things are part of our decision-making around infrastructure. So civil engineers, which I'm now one of, have responsibility for designing, building, operating and managing our infrastructure and built assets in perpetuity. And I quite like this picture of the city of Liverpool, because what you can see is up in the top left-hand side here, you've got energy turbines. On the right-hand side, you've got what looks for all the world like a communications tower. But in front of you, there's cranes building new things. There's some old warehouses down here that are probably 200 or 300 years old. There's modern buildings. There's a port that's been operating for hundreds of years. And that really gives you this sense of infrastructure as this sort of interwoven kind of kaleidoscope. So in order to keep it going indefinitely, we need insights, and insights from data, increasingly from digital twins and cyber physical systems. So I'm going to talk a little bit about that now. So essentially, cyber physical systems or digital twins are a smart way of adding value to both our existing and our new strategic assets. And what we mean by a digital twin is essentially you have some kind of virtual representation of the physical thing. It doesn't have to be a 3D model as shown here, but you have a virtual representation of it, which draws on data that is coming from the real physical twin. And then we use that data, we analyse that data to provide insights about the physical thing and inform interventions upon it. So essentially there's this sort of feedback loop between the physical twin and the digital twin, and then back to the physical twin. And it's this sort of live interconnection that makes something a twin rather than just a model. When I say a live interconnection, that doesn't necessarily mean that data is streaming every second and that decision making is happening every second, but nonetheless, the physical twin is being fed with real data from the digital twin is being fed with real data from the physical twin. And we get that data by adding sensors to our infrastructure or drawing information about our processes and so on. And that's what we call smart infrastructure in my centre, the Centre for Smart Infrastructure and Construction. So in CSIC, we think about all of this across sort of 4 phases of the life cycle. So performance-based design, transforming the way that we construct our assets, managing and operating our infrastructure as a system of systems, as I said, and then thinking about how infrastructure serves our cities and our communities more broadly. And that's all based on the use and development of appropriate sensor systems and data capture tools that informs data-driven decision-making and helps us to derive value from that. And the opportunity really here, I can't do better than quote Lord Kelvin, who back in 1883 said, if you don't measure it, you can't improve it. And we really need to learn from the real performance of our physical infrastructure so that we can inform all of our decisions about it, whether it's in design all the way through to operation and decommissioning. And by using data in that way, we can reduce uncertainty about our decisions, and we can create smarter infrastructure solutions for more resilient cities. And we can use that data and information to help us address the challenges of resource scarcity, carbon, and the need for resilient infrastructure. And for those of you that haven't seen it before, the picture on the right-hand side there is the Milo Bridge in France. If you ever get the chance to go and see the Milo Viaduct, I highly recommend it. It's an amazing structure. Now we can get data from a whole range of sources. So the obvious sources are, sensors that are physically attached to whatever it is we want to monitor, be that a bridge or a road or a sewer or a train or a car or what have you. We can also use what we call remote sensing. So that's everything from a laser scanner or a drone or a vehicle mounted sensor all the way out to satellite data. So, we go from things that are attached all the way to things that are monitoring our assets from, several hundred miles up in the atmosphere. We can also use data about processes. So we might use time and motion studies. We might monitor traffic moving through a city. We might monitor our construction processes to look at how efficient they are, for example. And we can also use social media and other kinds of data. And that's really useful for understanding things like the loading on our infrastructure. So how much is infrastructure needed? But it can also give really helpful information in the middle of some kind of environmental issue, like, for example, flooding. So there are some really nice examples out there of people using geolocated tweets and Facebook posts to track how floods are progressing and also to inform people about the progression of floods so that they can encourage people to move out of danger zones if they need to and so on. So, all of these sources of data are valid and relevant and interesting and helpful in managing our infrastructure. The challenge in the world I operate in is that we're not necessarily very good at using data well. So civil engineers have been collecting data about our assets for hundreds of years. The challenge is that often that data is collected, looked at once, and then archived, either on paper in a filing cabinet, which is the traditional way of doing it, or on what I call electronic paper, so PDFs. That is definitely not digital data. Or even if it's digital data, it's often in systems from which it's hard to retrieve the data, or where there is insufficient metadata about, how that data was captured, what it was captured for, what the devices were that we used, and so on and so forth. So one of the things I talk about a lot when I'm talking to civil engineers is that data curation is really important, because without data curation, without understanding all of that metadata about the devices that we used, why data was captured, where it was captured, when it was captured, what the conditions were when it was captured, all that kind of stuff, we can't make good sense from it. If we've got the data though, and we are able to access it, then we can start to look at long-term trends in the data. And when I talk about long-term trends, I'm not just talking about, things that might happen over days or weeks or months. I'm potentially talking about things that might be happening over decades and centuries, which in the context of long-lived infrastructure is still very important. Problems can build up over decades that then manifest themselves in a matter of minutes or seconds. So we need to understand how our infrastructure is performing over the long term. And if we can do that, if we can capture those trends and start to understand them, then that can really inform our decision making and help us to deploy our resources in the most effective way possible to keep the services that our infrastructure delivers going, because it's not about the physical assets themselves, it's about the services they deliver. And there's a whole range of things that we can do with better data. So we can improve our design, we can calibrate our design models so that we use less resources, or we make our assets more resilient to whatever shocks they might be seeing in the future. We can reduce waste in construction, we can improve the quality of our construction, we can improve the delivery of our construction by reducing the risk inherent in it. And we can indulge in, we can perform whole life value-based asset management. So rather than react and respond to problems with our assets, we can predict where issues might arise and prevent them or treat them or manage them. And then finally, we can meet the infrastructure needs of our citizens by modelling and understanding what the demands are on our assets, what their condition is, and thereby deliver social value to society. So today I'm going to mostly talk about the things on the right-hand side of this diagram, operations and maintenance and smart city systems. And I'm going to talk about whole life value-based asset management in the context of some aging assets. I talk a lot about bridges, not because they're the only thing we look at in CSIC, but because they're very tangible things. You know, everyone's seen a bridge, everyone's crossed a bridge, everyone knows what a bridge is. And the thing to be aware of is that a bridge isn't just a single asset. So obviously we have to think about the bridge itself as a single asset down at what we call the project level down the bottom here, and its condition. But we also have to think about it as part of a network. So part of a transport network, be that a road network or a rail network. So it's providing a service as part of a network. So the importance of that bridge is going to depend on where it is in the network, how much traffic it carries, whether there's an easy diversion route, for example, if you had to close the bridge or not. So how important a bridge is very much is about the context in which that bridge is operating. And that's the network level piece. And so you need to understand the condition of the network and the network's ability to deliver a service, which is informed by an understanding of the condition of the individual assets themselves. The challenge that we have is we often don't have good data about the condition of our assets. So as I said, most of what we build in infrastructure lives for a long time. To speak specifically about bridges, for example, Network Rail, which is the British agency that manages our physical railway in this country, they own and look after 28,000 operational bridges. Half of those were built before 1914 and are still in operation and are still carrying trains. Now, as you can imagine, the records that we have about the design of those bridges, very, very patchy indeed, because, you know, if the records ever were archived, there's every chance that they've been lost in a fire or a flood or, you know, what have you. So we have very patchy records about a lot of them. We have very little in the way of maintenance and management information over time about them as well. Until recently, we haven't had the kinds of sensors that you need to really understand the condition. Now, the digital revolution that we're experiencing now and have been over the last couple of decades or more has created the opportunity to actually generate lots of information about our bridges and really understand their condition. The challenge that we have, and perhaps this is something that colleagues in the Cape network can help address, is that often those sensing solutions are quite expensive. So if you've got 28,000 bridges to manage, you can't afford, certainly with current sensing solutions, to have them all fully instrumented. Now, you don't necessarily need to, because as I've said, the criticality of a bridge is based not just on its condition, but on its location in a network. But even if we look at all of our critical bridges, it's very difficult often for asset managers to have the resources to deploy on sensing all their bridges when they've also got to invest in maintenance and so on. So as I say, condition is often a bit of an unknown, partly because we have infrequent inspections is the best information we have about them that are done by humans. And obviously, even if the same person goes to the same bridge twice, you know, if you're going to a bridge once a year, you may not remember exactly what it looked like when you wrote down there's a crack on the parapet. You know, how long was that crack? Has it grown? Oh, I can't really tell. It's challenging often to make the business case for monitoring infrastructure because it's about averting problems often, and problems averted often are underappreciated. And we don't have a systematic framework to effectively manage our infrastructure under these constrained resources. So colleagues at CSIC have been looking at systems for actually carrying out a strategic risk analysis and identifying thereby which bridges are highest priority to manage and how we invest in that. So sorry, which bridges are the highest priority for monitoring and how we invest in that. And this is largely based around strategic risk analysis, which again is something that often is not well appreciated, certainly in the civil engineering community. You know, we often find people saying, how much is it cost? Is it going to cost, rather than how much is it going to save me, or what's the value of doing this in the long term? And risk assessment really is about not just likelihood, which is what people often focus on, but also consequence. So if something happens rarely, but causes deaths or derailments and massive disruption to a network, for example, then that's a high consequence issue and needs to be taken account of. There's also, you know, consequences made up of a number of things, like can you reroute the traffic? How much impact does it have in terms of loss of service? Is there an impact on the environment? So all of these things need to be taken into account. And once you've understood that, then you can understand what the different routes to risk mitigation are. Do we need to mitigate risk? Can we mitigate risk? And what's the cost of mitigating the risk? And what's the cost of not mitigating the risk as well? So that then helps us to prepare a business case for monitoring. And I'm going to talk a little bit now about some of these issues, because the challenge with a business case for monitoring is it's all very well to have a business case, but you have to have the money as well. So I'm going to talk a little bit about prioritising bridges for monitoring and how actually better information about bridges can help us with this in the context of climate change. Because it's very important to consider future scenarios when we are thinking about managing our infrastructure assets. So obviously, in the face of climate change, we are seeing more frequent heavy rain events happening. Quite a lot of these happen in summertime. And again, to take the railway as a case study, 3,500 kilometres of our railway in the UK alone is at risk from surface flooding, and just over 1,000 kilometres are at risk from river flooding. And it's estimated that this could rise substantially in the next 50 years. And in the past 5 years, that's caused 1.3 million hours of delays on the rail network. And we've had 2,250 flooding events on the railway. Now, one of the challenges with this is an issue called scour. So scour is what happens when you get very high water flows down a river and it starts to undermine the foundations of the bridge piers, so the columns that the bridge stands on. And there have been 140 bridge failures over the period of 1846 to 2013. So that's roughly one a year. But these things, again, are likely to get more frequent with climate change as we get more severe river flows due to more severe flooding event or rainfall events. And at the moment, it's anticipated that 1 in 20 of our bridges are likely to be at high risk of failure due to scour by 2080 if nothing is done about it. And that will have between 20 and 65 million pounds worth of scour risk mitigation expenditure required. And it's already resulted in 10 full collapses and 30 partial collapses of local road bridges in the UK in 2020 alone. So as you can see, this is not something that is just speculative, it's real. And one thing to note is that often our bridges don't just carry transport. So this is an image from the Tadcaster bridge failure, which happened about 4 years ago now, I think. And what you can see here is it didn't just carry a roadway, but it carried pipes, it carried communications cables, it carried power cables, it carried all kinds of things. And actually in the middle of that severe flooding event, I found out just the other day that the county police force's main comms line ran across this bridge. So when the bridge failed, they lost their main comms line and they were back to relying on, just relying on radios and so forth. So the impact of a bridge failure can often extend much further than just the transport network. So we need to think about not just the current condition of our assets, but also their resilience to future challenges. So this image on the right here shows what I was talking about. So you have the bridge pier, which is the column. And as the river flows down, if the water is flowing fast enough, you start to get what's called scour. So you start to get the sediment at the base of the pier being washed away. And it's very hard to see and identify because you've got to look through the river water at it. Often it's inspected by sending divers in to take a look, but obviously you can't do that in the middle of a severe rainfall event and a severe flood. So it's usually unmonitored during the period of severe rainfall. So we have to think about actually how do we understand how resilient our bridges are to these future climate impacts. So that involves climate predictions, it involves hydrologic modelling, estimating the river flow in different scenarios, and then predicting the scour depth for that river flow and categorising the scour risk. And here we've got an image that shows you the predicted peak flow for the River Great Stour at 4 different locations where there are 4 different bridges. And those peak flows are everything from about 3.5 cubic metres per second all the way up to about 23 metres per second. And what you can see is for the Green Bridge, for its peak flow, it's estimated that within about 36 hours, 2 of the piers on that bridge will have a substantial risk of scour failure. The 3rd pier actually will be fine regardless, but 2 of those piers are at severe risk of scour failure within sort of 36 to 48 hours of a peak flood. And interestingly, for the same flow rate, the Blue Bridge has a very high chance of failure, even if that flood only lasts for 12 hours. So suddenly we've prioritised between these 2 bridges. They're both at high risk, but the blue one is at really severe risk. So you might think, well, okay, the yellow and the orange bridges are fine then. But actually, when we look at it, we find that's not the case. So the challenge is that the orange bridge actually has much shallower foundations. And so again, for its peak flow rate, there's every chance that that bridge might fail even after just 12 hours of flooding. So this bridge and this bridge have the same risk of failure, even though their flow rates are very different. So that highlights the fact that we really do need to understand the condition of our bridges, and then we need to be able to monitor that condition going forward, and to combine that, for example, with modelling around weather conditions and weather predictions. So we can start to look and see, well, actually, we know there's a storm coming. We know these bridges are vulnerable. Have we inspected them recently? Do we need to stop putting traffic across them during the storm event? Should we, which bridges should we prioritise an inspection for immediately afterwards, and so on. So climate adaptation really needs to be part of our asset management strategies going forward. And that brings me to digital twins for structural health monitoring. So one of the challenges that we have in civil engineering is that we can generate huge amounts of data from different kinds of sensors. And the issue with that is, how do we process it quickly enough to make informed decisions? So we've been looking at developing digital twins for infrastructure. One of the digital twins we have is for our civil engineering building. Now, obviously this is not at the kind of risk of those bridges that I've been talking about, but it's an interesting case study because it's our building, so we can cover it in instrumentation. And what we've done is install a number of different kinds of sensors on this. So this is showing you the digital twin dashboard for the strain sensors that are on the steel frame of the building. Now, unsurprisingly, there's very little of any interest going on here because we're not in the middle of a windstorm, which is where most of the loading comes from in a building. But nonetheless, what this shows is that you can look around and you can potentially click on a sensor, see the data that relates to that sensor, and so on. What this shows is the data and information about our ground source heat pump and the borehole in between our 2 ground source heat pump boreholes. So we've got 2 boreholes going down here, and then we've got a kind of dummy borehole here where we've just installed sensors. And the key thing with this that we wanted to understand was, what's the capacity of our ground source heat pump to heat and cool our building? And is there an issue with the ground, with the temperature saturating between the boreholes? And so this data is actually being used by estates management to consider the viability of ground source heat pumps for the whole of the West Cambridge campus. And then lastly, we've created a digital twin for this railway bridge. Now, this is a bridge that we instrumented whilst it was being built, and it's covered in fibre optic sensors, it's got video cameras, it's got accelerometers on it, and it's got something else that I can't quite remember at the moment, a whole range of sensors. The key thing about this is, again, we can generate gigabytes of data off it in a day, and how do we manage that? So this just shows you the digital twin for our bridge, and this is a little video showing you how the digital twin works. So you can see the number of trains that cross the bridge each day, and for a given day you can select that and you can see when the trains cross the bridge. And then you can also see a video for every single train that crosses the bridge. Now, this is important because we use that to chunk the data so that we only capture the data that is interesting, because we're not interested in the 45 minutes between trains when nothing's happening. And then we can capture the data from the different accelerometers that are on the bridge, the different fiber brake strain gauges that are on the bridge, and then feed all of that into a range of different models that we have of the bridge to understand its behaviour in the longer term, and start to pick up differences in the bridge behaviour over time. And if I could get my, yeah, there you go. So this shows you then some of the modelling that we've done with the data, where you can start to see which strain gauges are exhibiting strain as the train crosses the bridge in a much more visual way. And then this next slide shows you some of the information that we have fed into an FE model that shows you in much more detail what's happening with the bridge. So that's a sort of single asset viewpoint. What happens when we come to cities, though? Because cities are much more complicated and they're full of humans. And that human element is important for two reasons. One is we humans are quite unpredictable creatures. So we're much harder to model than the sort of the physics of bridges. But also, we people are occupying cities. So data capture about us brings with it a whole range of governance and ethical issues that we need to take account of. Some of you might be aware of the Centre for Digital Built Britain, which has its last day tomorrow, I think, but has been an excellent 5-year programme centred at the University of Cambridge, but very much working with industry to look at digitalisation for our built environment. And they came up with these Gemini principles, which basically say that a digital twin, to be valuable, must have purpose. So it must deliver genuine benefit for the public good. It must create value and it must provide insights. So it mustn't just be a toy. It must be trustworthy. So it must be secure but open, and there's a tension between those two things, and built on good data of an appropriate quality. And it must function. That sounds really obvious, I know, but not always. So part of functioning is that data must be able to be shared between different twins, for example. That the data must be well curated, coming back to what I was saying earlier, and that the digital twin must be able to evolve as technology evolves, because you'll be very aware, you know, that technology moves very fast, whereas from everything I've been saying about infrastructure develops very slowly. So we have within our industry this sort of tension between assets that are going to live for 100 years and sensor systems that may only have a 5 or 10 year life, and how do we manage the interface between those two things? So crucially, digital twins in a city context in particular must create public value through responsible digitalisation in the urban built environment. So this is all about things we need to know. So what technology do we need to use? How do we get data from it? What is it we're trying to understand through that? But then also how we need to use it. So we need to govern our use of data and our digital twins. And we need to think about the ethics of what we're trying to do. We need to understand whether there's any bias in our data inherent in, you know, what we've decided to collect. Are there any communities that are being left out, or are there any important kinds of infrastructure that we're leaving out of our collection, for example? That said, digital twins are immensely powerful and useful tools. So particularly in a city context, we often govern and think about our infrastructure and our planning needs and so on in silos. But the reality is, as I said before, all of these things interact with each other. So we did a pilot project in Cambridge where we looked at this challenge of the fact that we have severe congestion in Cambridge, which brings with it an air pollution problem, but we also have an energy infrastructure challenge. And at the same time, our city is growing substantially. So we have new homes and new jobs, many of them projected in the next 5 to 10 years, which will put more demands on our energy infrastructure and increase congestion. So how do we manage that, and what are the interventions that we can make? Well, one of the things might be, for example, seeking for all cars to go electric, but the challenge with that is, and I'm going to skip one of our examples here, the challenge with that is that if all cars go electric, where do we charge them? Well, if they're all charged at the workplace, that's going to put severe strain on an already constrained grid in particular places in the county. If they're all charged at home, then that strain goes elsewhere in the county. Now, that's really helpful to know because it helps us decide where to invest in our energy infrastructure, for example. Other examples that we looked at included the potential for home working. Now, obviously, we did this before the pandemic. We massively underestimated the potential for home working. But understanding, the potential for home working, depending on where jobs are and where people want to live, means that we can do things like where we think job roles are amenable to home working, encourage the creation of communal workspaces so that people don't have to travel into the city centre as much. So digital twins can really support decision making. They provide utility in terms of managing data and analysing data and presenting it. They enable us to do things like optioneering and strategic planning. They can help us to evaluate and measure, for example, how much materials in a design or how that's reflected in what and how we build it. They can help with operational management and also long-term system asset management. So there's a huge value in digital twins if we use them right. And the key thing to remember about them is they must have a purpose. I don't really have a lot of time for carbon, so I'm just going to say a couple of things very quickly. You'll all know about the targets of net zero by 2050 and so on. The big thing about carbon dioxide is that it persists in the atmosphere for 100 to 200 years. So every ton of carbon that we emit today is going to be there warming our planet for a century or more. So we need to save as much carbon as we can, as quickly as we can, and do as much as we can with existing technologies, while of course researching future technologies. And the key thing there in terms of sensing and the sorts of work that you guys do is that we need to be able to measure and understand our carbon now. In order to inform decisions around what we should build with, how we build, how we optimize the design. So if we don't have good measurement tools, then it's very hard to take action and minimize the carbon that we have. So the things I've highlighted on this slide in orange are things where I think the world of sensing and measurement collides with the world of carbon. So it's things like being able to control processes, use robotic and automated processes where they can be more accurate, monitoring and managing construction processes and asset health, for example, measuring, monitoring and reducing resource use and carbon, using digital tools to track materials as they come onto construction sites or track materials as they move around the country so that we know when they're going to be delivered. All these things are really crucial in helping us to control our carbon emissions. And if we don't measure it, we can't improve it. And at the moment, sorry to say, whatever we think, we're not measuring our carbon footprint well enough at the moment. Part of our ambition to do something about that is this carbon reduction code for the built environment that we've developed, which I won't dwell on too much here, but just rest assured that good things are happening out there in the world in terms of carbon measurement. People are trying to improve it, but we definitely need the help of groups like yours to help us do that better. So I've talked about why infrastructure matters. I've talked about infrastructure as a system of systems. I've hopefully given you a bit of a view of kind of how we want to use data to help us better manage and understand our infrastructure assets so that they can serve society better. And I've talked a little bit very briefly about carbon, but I just want to leave you with that thought about the value of infrastructure. Why does infrastructure matter in our societies? Well, it matters because it allows the provision of all those services that make life more pleasant, more fun, more economically prosperous, and so on. Thank you very much. Darping, you're muted.
Mute. Yes, thank you very much, Jennifer. Yes, that's a wonderful talk. It's excellent. I was amazed at how you managed to get all the things, 7 topics through in 45 minutes and with such a clarity.
I talk fast.
Now, okay, I will run faster then. And so the floor is open for questions. Any questions? Yeah. I think this touches a wide range of the things and is linked with us living environment on the daily basis. So you might have some feelings. If not questions, comments, anything?
If people are feeling shy, then I'm going to ask Michael, if he's still on the line, why he's got a picture of bridge piers.
Yes.
Because I was inspired by your talk. So I actually took this a couple of days ago, Jennifer. So I thought I'd put it up because actually on this bridge there is evidence of substantial repair to one of the abutments quite recently, possibly within the last few months. and could be related to the scouring that you were talking about. So I thought, hey, I took this about 2 days ago. I need to pick it up and put it on there to show you we're listening. But while I'm talking, and thanks for spotting. And if you can spot and remember which bridge it is from the picture, you'll be.
It's somewhere in Cambridge, I guess. It's not the rail bridge because the piers are too close together. Or is it the St Ives Bridge?
No.
I give up.
No, it's the River Eden.
No, don't know where that is.
Flooded a lot. Anyway, it's in Cumbria. Yeah, I was going to say, but in generating this vast amounts of data, I guess the question is whether you have a view on whether we store the whole data, which might take up a lot of server space, and storing data in servers has carbon impact as well, or whether you would store some derivative of the data, just the analysis, or what's the view? Because if we're storing data for 100 years, there is a significant carbon impact of keeping that spinning.
Yeah, so that's a really good question, Michael. Thank you. And you're absolutely right. Data has a carbon impact. So I hate, for example, the idea of a data lake where we just measure stuff and accumulate it and then send some clever bot in to sort things out, because actually that never happens. And it becomes far too unwieldy far too quickly. So the crucial thing, if we're going to do any kind of monitoring, is to think about what are the problems that we think we're going to have or that we need to solve, and what's the data that we need to do that. And then I think you need to take an evolutionary approach to how much data you capture. So I showed you on our bridge, our rail bridge there, that we actually use cameras to clip the data. So we know when a train is approaching. We can also do that actually from the data, from the measured data on the bridge, but we know when a train is approaching, and we know when it's leaving the bridge. And we can use that and also sort of sensor data to only record the data that is of interest, because an hour between trains, there's a lot of nothing happening. So thinking about what data is actually required and what's not, and only storing the stuff that's required. We do quite a lot of processing at the edge where we can. Now, the challenge with that is if you're sort of effectively in doing that, you're throwing away some of the raw data. There is a risk in that you lose something. So what we tend to do is store everything on things that are new to us, and then gradually work out actually where the value is, and then start to only store the things that are of value and throw away, the dross, as it were. When we think about something like a bridge that's got to live for 100 years, ultimately what we might want to do is just store small amounts of strain data. You might keep deep records for the last 2 months, but then only store, a day's worth of data a month back in history or something like that. So you have to take a sort of progressive approach to how much data you store and how long you store it for. But the important thing for very old assets is you've got to bear in mind that in 100 years' time, someone else is going to have the problem of wondering what on earth was done with that bridge if we don't have good records. Because I could have given a whole other talk about an old bridge that we monitor up in Leeds, where loads of stuff has been done to it, because you can see it all, just like you could see the repairs to this bridge. But we've no records as to who did what, when and why. We just know it was done sometime in the past.
Yeah, great. Thank you.
Thank you very much, Michael. Any other questions? Jennifer, I just have some question, maybe you could help. I really like the ways you put it. The infrastructure is a system of systems. And I also very much like the measurement part. I think it's awareness of the people. People are being in the infrastructure or mostly being passive. They are not really aware what's going on, and the measurement make us aware of it. And by being aware of it, we can make a sense of it, we can manage it. I think you put it, totally understand. So we can manage the system or the system of the systems. But this is still on the side of the man-made structures we are operating. But we are also, this is immersed in an environment, in the natural world.
Yeah.
So how do we close the loop? That's the question.
That's a brilliant question, Dopping, and that's sort of in some ways less about measurement and more about societal decisions. So there are two things around this. So an obvious topic to take, for example, is flooding. So we have increased flood problems, and that's for two reasons. One is climate change. There's more moisture in the atmosphere, there's more rainfall and so on. But the other is we've increasingly paved over our environment. And this is very true in cities. So lots of us have paved our front yards in order to park our cars on it, for example. There's a lot more hard standing. And what this means is that when it rains, there's nowhere for the water to go except for down the streets and into people's houses. So we're starting to talk much more about natural approaches to flood management, for example. So can we use our floodplains again rather than walling the river off from them? Can we use salt marshes rather than hard sea defences, for example? There's a wonderful example in the sort of in Asia where mangroves traditionally protected coastlines, and then a lot of the mangrove forests were cleared so that cities could have access to the coast. But of course, what that brought with it is a lack of resilience to monsoons. So mangrove forests are now being restored to act as a natural flood barrier. So we really need to think about ourselves as part of a planetary system of systems. And if we only think about our built environment and ourselves, and we think that we are in some way separate from that, then we're kidding ourselves. Because obviously, we have had an impact on our planet, and our planet is now having an impact on us. And the more we think about, we're starting to see a lot more now about things like, for example, bee bricks being required in buildings. And a bee brick is just a brick with lots of holes in so that solitary bees can nest in it, or swift boxes being installed on buildings. So that's and green roofs. So the building I'm standing in has a blue-green roof, so it captures water, but it also has plant life on top of it. So we are starting to design our built environment assets much more with nature in mind, both nature in terms of how it can help us reduce the impact of things like climate change, but also how we reduce our impact on nature through our built environment.
Thank you so much. I think that's a brilliant answer, and it's just also a long way to go. We are now getting more and more depth to the nature, and then we also, if we can manage to impact the nature, or really make a real impact on the nature and control the world, that's all the natural world that we live in, that will be even better. But I can see it's many years down the road. Yeah,
there's a sort of change in philosophy. So our sort of Victorian forefathers, I think, were very much about how can we control things, and now we're realizing that we sort of have to, in a way, collaborate with nature. We can't exactly hold it back. We've got to work in concert with nature.
Concept, yes. Thank you very much. Any other questions or comments? If not, let's thank Jennifer for the brilliant talk. Thank you very much.
You're most welcome. And if any of you have a desire to fix a sensing problem, one of the big problems we can't tackle at the moment is detecting corrosion of steel that's hidden in concrete. So if anyone has any bright ideas on how we monitor corrosion, then do get in touch.
I think we can maybe invite this as one of the Cape's grand challenge.
There you go.
Put forward to the people. We can work together on that. Yeah, and invite from the university or beyond, see if there's any brilliant ideas we can tackle it. Brilliant. So this is the end of the talk. I would like to mention next talk, which will be on Wednesday, the 27th of April. And it will be given by Tom Watt, Claudia Mao, and Philip James from GSK Consumer Healthcare. Probably you heard, they will have a new name very soon called Helen. Helen, I think they are building the world's largest consumer healthcare company. And their talk is Consumer Healthcare, Finding Research That Changes the World. So Wednesday, 27th of April at 1400. So thank you very much, everybody, for attending this lecture, and I'm looking forward to see you all next time. And once again, thank you very much, Jennifer, for the brilliant talk. Thank you.
Thank you for having me. Okay. Bye, everyone.
Okay, bye.